Welcome in. All right, so power, right? So now I want to talk about power in fluids as they're flowing through. Now, I'm going to make the assumption that you're familiar with Bernoulli's equation in here because I want to glance back at every single term here and just let you know how you can come up with a power, okay, result in terms of the calculations. Now, for Bernoulli's equation, okay, so if you wanted to get a déjà vu on it, I'll put up a link up above there for you. And now each of these terms, you may recall that it is related towards kind of energy, right? So Bernoulli's equation is kind of like conservation of energy. And if you note, so all of these terms, so although this is pascals, we can of course write pascals as simply Newton per meter squared, which is coming from pressure. And then of course this also can be written as joules per meter cubed, right? So that's something that we have in here, okay, and I talk about in that video that I pointed out. Now, if you take the units for here, so once again, you can come up to exactly the same unit of joules per meter cubed. And then again, so if you take this, you're going to get joules per meter cubed. Well, if you're going to talk about power, so recall that power was defined as, now this is capital P instead of small p, at least that's what I use. So capital P is power, and then small p I use for pressure. So for capital P, we know that pressure, okay, or we know that power is equal to the transfer of energy, right, per unit of time, okay, that passes us by. Now this is, of course, can be captured in terms of the amount of work, okay, that you put into over the amount of time that passes by. And the unit, which is watts in SI units, are nothing else but joules per second. That is the actual definition of a watt. Now, if you look at here, so these particular units that we have, joules per second, and then you compare it to the units here, which is the energy that you have, and this is energy per unit of volume. Now, something interesting will happen. Now, notice that if you take your volume flow rate, right? So if you take this, which is the amount of volume that flows by per unit of time, so how much of a fluid is actually flowing by. Now, if you recall, so this has units of meters cubed per second, at least in metric standard units. Now, if you take the volume flow rate, and then all of a sudden you multiply it by any of these terms. So if you multiply it by pressure, or if you multiply it by this kind of the kinetic term, okay, or this by the potential term, so all of those are kind of energies with respect to volume per unit, well, what you're going to get, so if I would take each of these particular terms, notice what's going to happen. If I take pressure and I multiply it by the volume flow rate, so this is the pressure in the fluid, and this is how much fluid is passing by, okay, per each unit of time. And this, well, so as you can see here, this is joules per meter cubed multiplied by meter cubed per second. So the meter cubed and the meter cubed cancels, and hold on, what do I have here? Joules per second, which is nothing else but a watt. So if you take the pressure of a fluid and you multiply it by the actual volume flow rate, you get actually power result for that. And that would mean simply how much power do we need, okay, in order to possibly increase the pressure of something. So to change the pressure from one pressure to another. So if you're going to change the pressure, okay, and it's going up, you might need, so maybe like something like a pump, for example, where the pressure has to increase. So that means you're going to need power, right? So now what is that power? Well, that power is going to be measured by how much you want to change your pressure by, and then how, okay, so quickly this volume, okay, flow rate is moving along. So that's one of the components that we have. Now, if you take the other components, you're going to find something very similar. So if you would take now this component, which of course is in joules per meter cubed, and you multiply this component by the volume flow rate, you once again will get power. So that would be how much power, okay, is needed in order to increase kind of the kinetic energy. So the faster the actual fluid is going to flow. And then the last component, so this component right here that we have, well, so this component is related to kind of the gravitational, right, component of fluids. So if something is right here, okay, and it's kind of lifted up upwards again, well, you most likely are going to possibly need kind of power to push it through. And how much power would you need? Well, you're going to take this and you're going to multiply it by the actual flow rate that you have. So if you take each of these terms and now you multiply it by the volume flow rate, all of a sudden you have the total power, okay, per every single unit of time, okay, that you have added to each of these components. So very often we can write this. Now this is just one of the components right here, but of course we can take this and we can say this is 1/2 the density, okay, of the actual speed, right, which is flowing by, times the volume flow rate, plus, and then the last component, which is density times the gravity times the height, and then multiplied by volume flow rate. And all of this is actually equal to the total power that you would have. So the change in power that is needed. So that's pretty neat to be able to have this. So if I take this, and for example, I'm going to take this equation as it is, and I'm going to try to summarize it here for us. So all of this, so let me take this, copy it right there, and I multiply it by the volume flow rate right here, then this is going to give me what the actual power is, right? So that would have been the equation for the power that we have in these fluids. Let's take a look at an example. So here's an example. So here's kind of a fluid which is flowing through, and then we have a pump, right? So notice that we have a change in here in terms of the pressure that actually, okay, abides through from one side to another. So we have a pressure coming in, and then we have a pressure coming out. So there's a change in pressure. Let's assume that whatever the actual speed of the fluid here is equal to the speed which is coming out. So let's say that it's a 10 meters per second that we have. So there's no change, okay, on the speed side. And then clearly you can see that they're exactly at the same height. So there's no change in the height. So within here, so what we would have is if we wanted to calculate what the power is, so within, so this power, which is supposed to be equal to the pressure plus the component of the kinetic, which is related to the speed, plus the actual component which is related to the gravitational component of the height, which is h. We're supposed to multiply this by the volume flow rate. Now this is going to be the change that we have. We want to see like what changed. So it's changed on pressure. Notice it went from 1 times 10 to the 6 to 6 times 10 to the 6. So the pressure definitely changed. So we're going to have power that we need in order to keep this up. However, this component right here, because the actual speeds of the liquids are the same, there is no change in them. So that means coming in and coming out is exactly the same. So there is no power needed to maintain that. So this is actually going to be 0 in terms of the change. And the height within here, so the height, they're exactly at the same level. They're not at different levels in here. So that height change is also going to be 0. So there's no changes within here. So we don't actually have these two components. But we do see a change in the pressure. So that means this will boil down to the pressure and multiply the pressure by the volume flow rate. So now, how much change in pressure did we have? Well, the change in pressure was 6 times 10 to the 6, notice it's pascals, minus 1 times 10 to the 6 pascals. So that's the change in pressure. That's what we want to be able to see there. That's the power we need that the pump needs to exert to increase that pressure. The volume flow rate in here, we can calculate. So we do have what the speed is, and we do have what the radius, okay, of that, cylindrical tube is. So if I wanted to know what the volume flow rate is, so please recall that this is nothing else but the surface area multiplied by the speed that it is moving out, right? So this is out, okay, this is the area out, okay, that we have. So that's going to be pi. This is going to be times r squared multiplied by the speed. So we can substitute all of these. The radius was 3.5 centimeters. So don't forget, change it back into metric standard units. That's going to be squared. Multiplied by, this is the speed, which is 10 meters per second. So that's 10 meters per second there. And that is going to give me my volume flow rate. Now, of course, you know, this is just the total volume divided by the change k in time that we have. Now, so for this, if I calculate all of this through, so I'm going to have, so this is my pi. So within here, so I'm going to take pi times, and this is 0.035. We have to square that and multiply it by 10. So we have approximately, so this is the volume flow rate. Now, please remember, this shouldn't necessarily be a very big number because it is meters cubed per second, as long as you kept everything in SI units. So I'm going to keep that on the calculator because I'll need it, okay, in order to multiply it over here. So I have my volume flow rate over here. So let's put that in there. So that's going to be, you know, 0.03848, etc. So I have it on my calculator. So I'm going to take my answer and I'm going to multiply it by, now in terms of brackets, so this is going to be 6 times 10 to the 6, all right, minus, and this is going to be minus 1, so I could have just simply done that all in one go. That's fine, times 10, 1, 2, 3, 4, 5, 6. All right, now hit equals, and this is what my answer would be in here. So that those are the two. So my answer as a whole, so 192.4, Now keep in mind this is watts, so you can change it to kilowatts, which is approximately 192 kilowatts to 3 significant digits. All right, so that's actually quite a lot of power that we would need. So it's quite a big pump, okay, in order to keep that moving. But that's how we could calculate what the power actually is if we are given these things. Now, the only thing that changed was the pressure. There was no change of any kind in the other ones. If there was a change, we could certainly do those changes as well. All right, so that is it for this particular video. Hopefully it gives you some kind of a sense that you can relate and talk about power in fluids, okay, relating it back to kind of Bernoulli's equations, all of the different components, and all we have to do is multiply by the volume flow rate. Okay, thanks for watching. We'll see you in a future video. Bye, everybody.